Welcome back. Now that we have understood various parts of the velocity autocorrelation function and the property calculations, we are now going to turn back into some of the stuff that we talked earlier about different ensembles, because different physical situations require different kinds of ensembles. So, we are going to revisit them in terms of what kind of changes you have to make in your molecular dynamics code and your formulation of molecular dynamics, so that you can really get out of molecular dynamic ensembles. So, let us remind ourselves what ensembles that we are talking about and how we can do property calculation with respect to those ensembles that we have proposed earlier in our thermodynamics section. So, if you look at the first one is microcanonical ensemble, where the energy is constant. So, we have EVN. So, in this case there is no heat bath, there is no recalculation of the velocity vectors. We are essentially just looking at a simulation where energy is constant. It's because of that it is the simplest way of doing calculation of potential and kinetic energy. And then if you go towards different temperatures for the system, then you can even calculate some of the potential energy jumps created by the phase transition in that material, as long as the potential function representing that material is well designed. So, there is a dependency on the potential energy functions based on the potential energy terms, bonded and unbonded term, but now we begin with EVN ensemble, which is microcanonical ensemble. Then we go to TVN ensemble, where temperature is constant, and there has been a lot of literature in molecular dynamics, and I will discuss 3 different methods for the rescaling of temperature, because that is one of the most important quantities in order to come up with a system that will take care of the macroscopic properties, because the macroscopic properties heavily depend on the temperature as a driving force, especially things like phase transition induced by the temperature increase in solids, or even in the gaseous phase. If you go to very high temperature from gas, you can go to plasma phase. And so, again, that kind of transition where you are in a very high temperature plasma, you can also study that, but you have to have a right kind of temperature algorithm that we need to understand. And if you also remember, we are talking about thermodynamic temperature here, where we are looking at velocity of each particle, and that particle velocity has to be rescaled every so many time steps in order for you to get the effect of constant temperature. So, we will look at that, and then let us get into the constant pressure, because we are going to look at models that are applying different kinds of volumes, and if the volume changes, then as you know very well that the pressure will change. So, we have understanding of the ideal gases, the Charles law and the Boyle's law, which connects volume and temperature and volume and pressure, and also temperature and pressure, which are all connected quantities. So, we are going to look at some of those effects in the constant pressure. So, now the question comes is that if I have to reasonably calculate a macroscopic property, which is considering the pressure as one of the variable or driving force, in that case it could be martensitic transition, it could be fracture, it could be growth of certain fracture throughout the material, or it could even be pressure induced changes in the phase of a material. So, as I said earlier in my previous sections, that ice has 9 different structures, and they exist in different temperature and pressure regime. So, if you go to a glacier and go deep into the glacier, there is a very high pressure on the system. You will see different kinds of ice structure as compared to your normal ice that you have in your refrigerator, which is hexagonal packed structure. If you look at the cubic ice, ice 1, ice 2, ice 3, they are all different kinds of structural elements which are based on the pressure. And then of course, there is a whole bunch of things that you need to understand in terms of chemical reactions. So, if there is a NaCl which is your common salt, and you take that salt and if you put in the water, it solves in there is a solution of the salt in the water. That is a simple process of adding more atoms of NaCl into the matrix or substrate of H2O, which is essentially the water. So, if you look at that, now we understand that these are two different species, sodium chloride and hydrogen and water and the oxygen. So, the water is made out of oxygen and hydrogen atom, rock salt is made out of NaCl, which is sodium chloride. If you now connect them together, then you can see what kind of solubility will happen. So, we can also simulate those, and that comes under what we call as grand canonical ensemble. So, we now want to turn our property calculation discussion into the context of different kinds of ensembles. So, let us start with the canonical ensemble and look at the constant temperature issues, because constant temperature issue is important with terms of different kinds of dynamics that we look at. We understood earlier, for us to put the Nose-Hoover thermostat, we have to go to Lagrangian dynamics. So, let us look at it one more time. So, if you look at on your slide, you have MD in canonical distribution, which is TVN, temperature constant, volume constant, and number of particles. So, we introduced in Lagrangian dynamics, as you remember, a friction force psi t, and in this case we are looking at simple change in the pressure with respect to time, which is also looking into force minus the friction term. And if you look at the dynamics of the friction coefficient to get canonical ensemble, then you can again use this simple equation q d psi over dt summation over half m v square, which is kinetic term, and then this is the temperature term. So, the kinetic term and temperature term will give you the friction, which is added d psi over dt q, and q is the friction heat bath mass. So, we are essentially changing the mass of this friction coefficient, and that is where we are increasing the coefficient d psi over dt with the change in the mass. Large q is a weak coupling, so we are looking at that. And if you look at the dynamics at steady state, then you take the friction term out, which is d psi over dt is equal to 0. So, that gives you a good understanding of the Nose-Hoover model, where you are looking at constant temperature by adding a term which we call as the friction term, and that essentially is damping the vibrational element of the system. So, if you add another vibrational element to a molecule which is vibrating at a particular frequency, you can increase or decrease the frequency. Let us say if I increase the temperature of a system to a particular value, then you have to use the equipartition theorem to distribute that as a velocity into all particles. Now, velocity may drift based on the dynamics of different particles. So, you may see some particles having higher velocity and some of them having lower velocity, which we saw in our earlier VMDL, where we saw that some particles were very high velocity, some of them were low velocity. Now, in this case, we can adjust that by again rescaling based on the friction coefficient that we are adding to the dynamics. Now, if you look at the Hamiltonian in terms of the Nose-Hoover, then in this case the heat bath will have a energy plus heat conserved. So, in this case you start with H as total energy, kinetic and potential energy, plus you are using the square of the term which is counting about the friction, and then you have G K B T ln S, which is essentially the entropy term. So, if you look at the entropy term here, which is the differential of time with respect to logarithm of the entropy psi, then you are able to look at the derivation of equation of motion from Hamiltonian perspective. In that case, dr over dt is equal to p, and if you look at dp over dt, which is equal to which we are looking at the pressure term here in terms of dp over dt, f minus the friction term, and then if you look at the change in the friction term, you are looking at that with respect to the pressure term as well. So, what we if the system is ergodic, then stationary state is canonical, distribution. So, in that case now we go back to our statistical mechanics machinery, where we say okay, for this situation we have to use a particular term in order to account for the temperature, and that will be decided by the potential energy, the kinetic energy, and the term which is resistance. With that understanding, now we are ready to create property calculation on the constant temperature. Thank you.